I'm gonna stay seated. I was gonna do something, but I'm just gonna stay seated. Hello, everyone. Good evening, and welcome to the Speakers Night presented by the Royal Astronomical Society of Canada, Toronto Centre. Tonight's presentation will be Venus from Earth's Twin to a World Apart. My name is Rachel Ward Maxwell. I'm the second vice president of the Toronto Centre, and I'm so happy to have you join us this evening. I would like to begin by acknowledging that the RASC Toronto Centre is located in Toronto on the ancestral lands and territories of the Anishinaabe Nation, which includes the Mississaugas of the Credit First Nation and the Chippewa, as well as the Haudenosaunee Confederacy and the Wendat peoples, and is now home to many diverse First Nations, Inuit, and Métis peoples. Toronto is also governed by Treaty 13 with the Mississaugas of the Credit and the Dish with One Spoon Wampum Belt Covenant. As a settler, I am grateful to be able to live and work on this land alongside the Indigenous peoples with whom we peaceably share this land and who've cared for it since time immemorial. Now, as an astronomer, I often find myself thinking less about the land itself and more about the sky, which is why I really value these opportunities to stop, learn, and reflect on my relationship to the land and consider ways that I can connect with the land more in my daily life. Some of you may be joining from other locations today. We're all encouraged to always find out more about the peoples, treaties, and land that we live on. There are several resources available. Ones that I have found helpful are the websites whos.land and native-land.ca. Tonight, we are joined by Megan Russell, a research associate from the Planetary Science Institute. Since starting at the Colorado office of the Planetary Science Institute, Megan Russell's research has spanned volcanism on Venus to the characterization of ice on Mars. Megan serves on the science and operations teams for the SHARAD instrument aboard NASA's Mars Reconnaissance Orbiter, a spacecraft that is currently orbiting the planet Mars, and supports the science team for VENSAR on ESA's upcoming Envision mission to Venus, ESA being the European Space Agency. Her research also includes projects focusing on Mars, Venus, and the Moon as well. After completing a space science degree at York University in Toronto, she worked at Photosat, an Earth remote sensing company, and then went on to complete her Master of Science degree in Geophysics and Planetary Science at the University of British Columbia with Dr. Catherine L. Johnson. Megan loves all types of Colorado activities: rock climbing, hiking, river stuff, snowboarding, snowshoeing, ice climbing, and also martial arts. So please, everyone, join me in welcoming Megan Russell to the RASC Toronto Centre.
Hi, thank you so much for that introduction. So before I introduce myself a little bit more and get into Venus, I just want to start with a short experiment. So a couple of years ago, when AI generators became popular, I asked one to show me what a planetary scientist looks like. I tried prompts like scientist building satellites, planetary scientist processing data, or standing on the surface of Venus, and a pattern quickly showed up. The models had a very narrow view of who belongs in that role. And so here's a more recent result from that same experiment. I consider that kind of a partial success and improvement of the models of about 2 years ago. But this is not a story about AI. It is a story about us. These systems are trained on human-produced material, so they often inherit the assumptions and biases already sitting in our culture. And that turns out to be a useful way to think about Venus. For a long time, people projected familiar ideas onto Venus, and I'm going to outline those further in. And tonight, that's really the theme of the talk: how observation replaces projection. So I'm going to give a brief history of how we came to understand Venus, a crash course in radar, and where the next generation of spacecraft missions is taking us. So as Rachel already outlined, I have kind of a non-linear career path. I went to university, worked in industry, went back to university in Vancouver, and now I'm working at the Planetary Science Institute in Colorado. And so I took that road trip down from Vancouver to Colorado in 2021. And there's a picture on the left of my car at one of the many parks in Utah, right on that road trip. So yeah, I just wanted to point out my career path, which is nonlinear, and it's becoming a little less uncommon these days. So as a brief historical account of Venus is important because this planet played a role in technological advancements in the exploration of our solar system and close neighbors. And there's a commonly held notion that Venus is simply Earth's twin, and I'm hopefully going to convince you against this. So I'm going to compare and contrast the two planets, talk about radar. I'll go into more detail later, and present the questions and the answers, and the more questions, those answers brought about by past spacecraft missions and what the next generation of space missions wants to answer. And so planet means wanderer because they looked like little stars in the sky that appeared to wander with respect to the background constellations. And that this planet Venus was named after the Roman goddess of love, beauty, and desire. So it's very fitting that Venus was the first planet to be explored by a human-built spacecraft. And you might have heard of it referred to as the morning or evening star, and that's because as the next planet over, it's closer to the sun, and it always trails the sun in the sky by about an hour or more. So sunrise or sunset is when we're going to see it, and we're always going to see it in the east or the west, morning or evening sky, because of this. So Galileo Galilei sparked kind of modern observational astronomy in the 1600s. But how was the universe viewed before this? Here's a illustration of what the Ptolemaic view of the Earth was. It was placed at the center of the universe with the different planets and the sun orbiting around it, and then further out, the constellations. And you can see Venus right there. So this was a view that, there are many cultures that held many different views of the universe, and this was one of sort of the Western European world pre-1600s, the Ptolemaic view. But around that time, there were scientific advances in optics that started helping us reveal truths about the world around us, and most notably our solar system. And Galileo was one of the first, there were a few, but one of the first to point a microscope to turn telescope skywards. And he started noticing things that didn't really jive with this view of an Earth-centered universe. He observed some bright objects in our sky, like the rings of Saturn in the upper left there, and Jupiter in the middle, and its 4 largest moons that orbited around it. These are the Galilean moons, and I'm sure you know we can see them with good binoculars or even a cheap telescope, and they're really cool to track over the night sky over many nights. And that's actually how I kind of got my start in space science when I was really a lot younger. I was given a telescope and I looked at the craters of the moon and also the moons of Jupiter. And it was really cool to see how they just, they were in a different arrangement every evening, and that changed. And Galileo also looked at Venus, and he saw that Venus was very bright and it showed phases kind of like the moon, and it also changed in apparent size. And that also didn't sort of reconcile with that Earth-centered view of the universe. And these observations that were published back in 1623, they kind of started making their rounds in society. But the theological experts from the church at that time officially decided to reject anything that didn't really enforce that Ptolemaic view. And he was eventually sentenced to be burned at the stake. He did recant, and by some accounts that made him feel abjured, cursed, and detested. And he recanted, but not before allegedly muttering under his breath, and yet it moves, meaning the Earth is not stationary and it moves around the sun. So I just thought this was an interesting example of Venus in the role of pragmatism versus dogma. So spoiler alert, here's a modern day view of Venus. This is from a spacecraft in 2018. And this was the Akatsuki Japanese spacecraft. And this image shows not so much a naked eye view, like what you would see if you were traveling to Venus yourself, but there are imaging bands in that multispectral data that kind of highlight structure and compositional differences in the clouds. And there's a funny story about this spacecraft. Well, I think it's funny. It probably was really sad for a while, but it got lost on its way to Venus. It suffered an orbital insertion failure, and for 5 years, it kind of orbited the sun in safe mode. So it was put into a mode where it was safe and not trying to drain its batteries or fuel. Engineers were able to make communication with it again after 5 years, and they placed it into a different orbit around Venus in 2015, which was very exciting. And it actually began a successful science campaign studying the clouds and the atmosphere of Venus. And these clouds in this image are 20 kilometers thick, by the way. Oh, and that's an image of the spacecraft. Okay, so backtracking to the period of 1800s to the 1950s, people had known that Venus was shrouded in clouds, and that's all we kind of knew for a while. This fueled science fiction stories where imaginations ran wild, and Venus was actually often portrayed as some exotic, steamy jungle inhabited by beautiful women or disgusting beasts, as I've seen it written. And in true human hubris, they were human-centric aliens. The public views of Venus ignored even observations in the 1920s that kind of suggested that although it had clouds, it had less water in the atmosphere than we probably wanted it to. So it's starting to look a little less like Earth already, but popular media didn't really catch on. They really wanted to believe that Venus could be another Earth. And this is kind of summed up in a video of Carl Sagan, giving a somewhat sarcastic example of faulty scientific logic. Let's see if this plays.
The arguments, if we can dignify it with such a phrase, went something like this. I can't see a thing on the surface of Venus. Why not? Because it's covered with a dense layer of clouds. Well, what are clouds made of? Water, of course. Therefore, Venus must have an awful lot of water on it. Therefore, the surface must be wet. Well, if the surface is wet, it's probably a swamp. If there's a swamp, there's ferns. If there's ferns, maybe there's even dinosaurs. Observation, you couldn't see a thing. Conclusion, dinosaurs.
Okay, so if you search for that video on YouTube, you'll see a lot of clickbait articles. Carl Sagan believes there's dinosaurs on Venus. I thought that was kind of funny. Okay, so this is our solar system as we now know it. This is a diagram. The planets in our solar system are shown relatively to scale, like their sizes, but not the distances. They've all been compacted to fit on the screen. So we have the sun on the far right, which is huge. It's this big white sphere. And then we have the inner rocky planets, large Jupiter and Saturn right here as the gas giants, Uranus and Neptune as the icy giants, and Pluto's in there somewhere as well. Just want to mention that. Here's a close-up of the Earth and Venus and also Mercury compared to the surface of the sun in size. And so we can see Venus is next to the Earth, closer to the sun, but not that much closer, like Mercury. And it's in the same solar system neighborhood, which means it's created from the similar building blocks, so similar composition. In the early solar system, the building blocks for the planets were differentiated in the solar nebula. And so the Earth and Venus are probably made out of the same stuff, the similar density, and they're around the same size too. So I've introduced and discussed the historical allure of Venus, and now I'm going to outline the next generation of spacecraft that visited Venus in the 1960s to 90s and explain sort of the data and the observations that we got from them. So we did know in the early days of direct observations that Venus, it has a slow retrograde rotation, meaning it rotates opposite to what the Earth does, meaning that the sun will rise in the west and set in the east. And this is weird compared to Earth and most of the other planets. And we knew that it was bright and hot. And the Mariner series of missions, specifically 2, 5, and 10, did do flybys of Venus on their way to other places, and they were able to collect some data. And that kind of gave concrete evidence that there was no magnetic field, for one. And on Earth, we're very lucky to have a magnetic field because it protects us from long-term atmospheric loss, for example. And it entertains us, like the southern and northern lights and the role that it plays in that. And the Mariner missions kind of gave evidence that supported the theory that the surface was hot and atmosphere was like optically thick, and it had similar dayside and nightside temperatures. And that was kind of about it. So we were starting to see that Venus and the Earth are quite different. We know that the atmosphere from optical spectra had a lot of CO2, carbon dioxide, and there were some anomalies in the data that pointed that the atmosphere was also thick, but again, this wasn't a unique solution. It could be something else to explain the observations, something weird in the ionosphere, or even on the surface. So the observations that have been collected thus far, they needed a reconciliation. And Carl Sagan's 1960 thesis introduced a model to try to reconcile this. He proposed a carbon dioxide runaway greenhouse effect that was going on. And these observations would arrive, or this model would arrive at a solution that gave it a thick atmosphere, kind of explained some of the observations, and coupled with a hot surface, the atmosphere had to be as thick as maybe 20 to 100 times thicker than the Earth. So that would mean the surface pressure was 20 to 100 times what we experience on the surface of the Earth, just from the atmosphere around you pressing down. And that seemed pretty wild, almost unbelievable at the time. So the next suite of spacecraft to visit Venus used a special technology to image the surface called radar. And I'm going to introduce that here for those that aren't familiar. It stands for radio detection and ranging, and this is an active remote sensing technique that sends electromagnetic energy down to a target and measures the return. And it uses radio waves that are about centimeters to meters in wavelength. And clouds happen to be transparent at this wavelength, so you can see through the clouds on the Earth and also Venus. And so some of the applications of radar, they're very wide ranging, but for example, starting in World War II, it was used for the detection and ranging of objects. It's used in weather, it's used in sounding, so seeing into the subsurface of different targets, like on Earth, exploring debris-covered glaciers. We're starting to put this radar on drones as well to see into these glaciers. And it can also be used to image the surface of both Earth and other planets. And here's a diagram showing kind of the difference between optical and radar imagery. On the left is a color image, just using regular color bands that you would see. And then on the right is the same area imaged with radar. So this imaging radar kind of returns something that looks like just a grayscale image. So in terms of imaging radar, one technique that we've used is Earth-based radar. This is Arecibo Radar Observatory in Puerto Rico. You might recognize this from such films as Contact and the 1995 James Bond film. It did suffer a catastrophic collapse in 2020, and this is a picture by me when I visited in 2023. At that time, they were still allowing visitors to go there. There's a visitor center. And so that was really sad. We lost a really big instrument. But when it was in use for Earth-based observations of Venus, for example, it would send a radar signal to Venus when it was in view, and it would measure the return in the same location, just with a slightly different instrument. So it's sending a signal and it's measuring the return. And from that, build images and stuff, everything. You can also, that's an example of monostatic radar, and you can also use a second radar observatory on the Earth to measure the return. For example, the Green Bank Telescope in West Virginia, and this is called bistatic radar. So many applications on the Earth for imaging celestial objects. We also have space-based radar. And so I'm going to introduce synthetic aperture radar without getting too much into the weeds. But in this setup, the spacecraft is orbiting. It both sends and receives a radar pulse, and it's also moving. And so the distance that it travels over a target, when it illuminates that target, during the period when the target is illuminated by the radar, it creates a larger synthetic antenna, which has a bigger aperture, and it gives you a higher resolution image. So you're seeing more detail with this synthetic aperture. So the next suite of missions all had a radar instrument on board, like I mentioned. For example, the Venera series of Soviet spacecrafts that had both atmospheric probes and landers. And so they were more or less doing in situ measurements at very small scale, measuring the atmosphere over altitude or small areas on the surface of Venus with the landed spacecraft. The first one, Venera 4, sent an atmospheric entry probe through the atmosphere and made measurements as a function of altitude. And it stopped working at what was probably an altitude of 26 kilometers. above the surface because the extreme conditions of the pressures and the temperatures were so high that scientists hadn't been expecting them, but they did have models to indicate these extreme conditions. And this was kind of a result of a selective rejection of disquieting data, as Carl Sagan put it in 1969. So there was evidence that it could encounter these extreme conditions, but it seemed to be just too intense. And so they kind of rejected that and the probe stopped working. This is a picture of one of the Soviet landers, one of the Venera ones. So this was actually on the surface of Venus, taking measurements for quite a while in, I believe, 1967. Venera 9, one of the landers, returned the first image ever taken from the surface of another planet. And so this is the surface of Venus. I've talked to people over the years, and not everybody's aware that we do have pictures from the surface despite the extreme conditions that these spacecraft encountered. This is an image from the spacecraft looking down at the ground in kind of a panoramic view. And you can see there's a lot of large jagged rocks there, and the horizon looks pretty flat. And this image was beamed back 1 pixel at a time at an extremely slow data rate. This is the first color image of Venus. It wasn't the first color image of any planet. I think that was Mars, but this was the first for Venus by Venera 13 in 1982. And you can see slightly different surface. There are these large, flat, platey rocks with small pebbles. It looks quite yellow, probably wasn't that yellow. There's a color calibration stick in the scene. And it's looking down, and again, down at the ground. And this piece of material here is actually a lens cap that was on the lens of the camera to protect it during descent. And when it landed, a pyrotechnic charge would pop that lens cap off so it could start taking images. And this was important because for the next mission, Venera 14, it had an instrument to measure the properties of the rock, like the hardness and fault composition on the end of this little arm here. And the lens cap just happened to come down where the lens cap had landed. So instead of sampling the surface of Venus, it sampled the properties of that lens cap, which was, I think that was fixed for subsequent missions. Oh yeah, right there. Okay, so here are some surface images from those landers that have been reprocessed and reprojected, so they look more like what you would see if you were inside that spacecraft looking out across this alien landscape. And again, these two areas look quite different. We have these large platey rocks, probably old lava flows. And if you were in the spacecraft at the time, the weather report would go something like visibility 3 kilometers, temperature 465 degrees Celsius, pressure 94 bars, wind speed 1 meter per second. And this wind speed was backed out from measurements taken during an audio recording from one of these Venera landers. And this was the first audio recording from another planet. And again, that 94 bars of surface pressure would be like having a small car sitting on an area the size of your thumbnail. So it would be very crushing, and it's, again, very different from the Earth. One of these spacecraft also had a radar imaging instrument to image from orbit. And this is kind of a regional view at the time. It was about 1 to 2 kilometers resolution. And so we can see lots of interesting tectonic belts and a lot of other features here that we might not see as wide scale on the Earth. The next set of missions, the Pioneer Venus 1 and 2 missions, orbited Venus, and they collected a global data set from space, but this time elevation, surface slope, and the reflectivity of the slope or of the surface, again using radar. And the global elevation data set was about 75 kilometers resolution. So that was coarse, but we didn't have the same global resolution of elevations for the Earth at that time in the early 1980s. Pioneer 1 actually lasted 14 years, which was about 13 and a half years longer than its planned mission. So scientists were getting pretty savvy at that point, engineering-wise. The next mission, and still remains one of the biggest to characterize the surface, was the NASA Magellan mission to Venus. And I found this poem in the radar user's manual for that mission. Venus, sweet mystical star, Earth-like but hotter by far, no use to peruse unless you can use synthetic aperture radar. So that manual was all about how to utilize this synthetic aperture data from Magellan. And here it is. Here's a spacecraft. It was actually launched, quote unquote, from the space shuttle. It was released from the cargo bay doors of the space shuttle while it was in low Earth orbit. And then it made its way over to Venus. And so this was about 1989. And here's an illustration of Magellan arriving at Venus and settling into its science and mapping orbit. And it produced a global data set of synthetic aperture radar images, radar elevations, which were best by far at the time and still remain so. This is the most comprehensive data set of the surface of Venus that we still have. And it managed to go pretty much globally and measure everything, and with the radar, use different imaging angles or incidence angles for the imaging. So it had really good science applications. And just to compare the resolution of the radar data from Magellan, here's a picture of the surface of Venus from the Venera 15 and 16 orbiters, spacecraft, of what we think might be a field of shield volcanoes. And here's the same area from the Magellan spacecraft. So much higher resolution, you're seeing a lot more detail, and you can see, yes, these are small shield volcanoes. I measured them, they're about 1 to 12 kilometers across. And if we zoom in, we can see features on them, like little caldera in the middle. And you can see a lot more tectonic features on the surface, a lot of cracks in the surface, and also lava flows. So really good comprehensive radar images. It also collected elevation data over the entire surface. And here's a distribution of elevations for the Earth and Venus on the top. For the Earth, so the x-axis shows the range of elevations of the surface, so the topography, and the y-axis represents the percentage of the planet that sits at that elevation. And so on the Earth, we have a lot of elevations that are low. These are the ocean basins. And we have some elevations that are high, and these are our continents. So these sharp bimodal distribution of elevations is brought to you by the continents and ocean basins or plate tectonics. And Venus is here on the upper right. We can see it has a broad range of elevations, but unlike Earth, all the elevations kind of lie within a few kilometers of the mean. So we don't see this bimodal distribution that we see for the Earth. There are some high areas of what we call tessera, and these are sort of higher, maybe older and highly deformed areas on Venus. And it does have a few very, very, very large volcanoes, which are built by lava and possibly rising up in the mantle to produce dynamic uplift. So that's kind of what produces the higher elevations on Venus. And so this is another way in which Venus and Earth are very different, the elevation hypsometry. So with this new global data set, there were a lot more features on Venus that had to be named. There were chasma, volcanoes, different types of volcanoes. There were craters, there were high regions, there were low regions, there were weird linear features, there were ridges. And so 40% of these features were named after real women who existed and made contributions to culture and science. And the rest are feminine mythological figures. We saw a broad range of different types of volcanoes. This is a pancake dome on Venus. And you can see there's sort of maybe 3 to 4 of these pancake-shaped volcanoes. So they're very wide, very flat, very circular, and they probably all formed close enough to each other that they've all kind of formed as one, kind of like if you make cookies in an oven and you put the cookie dough too close together, they'll kind of form together. Each of these are about 30 kilometers across, and some of them got so big that the material in you can see in the upper northern section here, collapsed under its own weight, and this is probably what we recognize as a landslide. And so part of this volcano has collapsed. And so just another way that Venus and the Earth are different. Here's an image showing two craters, amongst other things. Craters on Venus are really cool. They have a large blanket of debris and rubble around them from when these meteors came through the atmosphere, survived that thick atmosphere, impacted the surface, and created these impact craters. So you see this really rough, high radar return material, as well as sort of finer scale, maybe dust that was created and swept up into the atmosphere and then settled down. So there's a big crater and a little crater, and in between them, there seems to be some sort of very long, very large lava flow. And on Venus, we also see these long lava flows associated with impact craters, and that probably has something to do with how hot the surface is. This melt generated from the craters can actually survive for a long time and create these very long flows. And craters are very important because scientists generally use them to date the surfaces of the moon, Mercury, Mars, etc., any airless body, or even Venus. And they assign surface ages based on how many craters per square kilometer, for example, there are. We can't do that on the Earth because we have a lot of different processes going on to renew the surface, like weathering, plate tectonics, vegetation, and that renews the surface and kind of erases these craters. And so what we found on Venus is that there were much fewer craters than expected. We only saw about 900 of these. And on Venus, on Mercury and other planets, that number is a lot larger. And so without some sort of process to renew the surface, like how were so few craters preserved? And that's one of the questions that continues today. Here's another interesting feature. I think I mentioned this before, but this is called a corona. And I've color coded it so that high elevations are shown in red. And so we have this ring of high elevations around that's kind of circular, and lower elevations are blue. And then there are a lot of different fractures that are associated with this. Some of them are radial, some of them are concentric, so following the topography. And in the center, we have a lot of volcanism. And this is kind of generally what we see with these types of features on Venus. We don't really see these types of features on the Earth. Here's another corona. This is Verdandi in something called the tessera plains. So areas that are extremely uplifted and deformed. They're kind of interesting for structural geologists to look at, and they create these really interesting patterns. And the corona here is quite circular, and it has that concentric ring of fractures with a really low elevation in the middle, and a lot of lava flows associated with it. So again, so Magellan showed us that the cratering record sparse, not as many craters as we were expecting. And there were no signs as we know them on the Earth of active plate tectonics to recycle the crust and create new surface and make a very young surface age. So based on the number of craters on Venus, we've assigned a surface age of about 500 million to 1 billion years old, which on the Earth, that's old. Compared to Mercury or the moon, that's quite young. And so maybe there were jungles at one point. Maybe we did have something else going on. People still don't agree on the mechanism by which the surface of Venus is renewed, and also explain the cratering record. But there are, there's a really interesting ongoing debate between different processes. So again, Venus and the Earth, a little bit different. So as one part of my master's research, I was looking for maybe signs of activity on the surface and signs of volcanism, and I used all Magellan data. And so this was one snapshot frozen in time from the early 1990s from this mission. And so this is kind of an example of how all of this data might come together in a scientific investigation of Venus. I'm a planetary scientist, but I specialize in geophysics, and we do like to do modeling. So I used higher resolution elevation data for Venus that was produced from stereo photos. So you can also take stereo photos with this radar data and produce elevations with them that were a little bit higher resolution than the global data set, but a little bit more sparse. There were a lot of holes in the data that we had to deal with. And so I took this data and I investigated a specific volcano on Venus, a volcanic dome shown right here. And it was so big and heavy that it was actually causing the surface to sag or flex underneath it. And we can see here, I've color coded it so high elevations are red, so you can see the outline of the volcanic dome there, and then this moat of low elevations around it in blue. And so using this signature of flexure, so the crust in the lithosphere is flexing underneath this, we can infer how thick the surface is underneath the volcano. And from that, you can say something about the heat flow beneath that feature. And so what we found is that this area has an anomalously high heat flow in this one area that we could make these measurements for, especially compared to what we would expect for the background or other features that were measured this way. So we can use these types of methods to infer maybe geologically recent activity on Venus. So the Magellan mission did a very good job of collecting a global data set and looking at everything on the surface, but we do continue to push the data to its limits. There were lots of questions that were answered, but there were lots of questions that were also created. And humans have kind of taken a hiatus from looking at the surface at such a global scale. There have been 2 more missions that characterize the atmosphere, but we haven't really had a geophysical mission since the 1990s. And so the next round of questioning and investigating will involve asking how old is the surface? Has it undergone massive volcanic resurfacing? Is that volcanic activity still underway? Do different areas have different kinds of rock? Because again, we haven't been able to collect the type of data that would allow us to answer that because the atmosphere gets in the way. And how does the atmosphere and the surface, how do they interact chemically? And there are lots of lab experiments going on now in Venus chambers that simulate these surface conditions and see what a rock does, for example, a piece of lava, when you put it into these conditions. And this has big implications for interpreting radar data as well. How quickly does that rock change under these conditions? What is the precise composition of the atmosphere and how does it vary with location and altitude? And when and how did Venus's runaway greenhouse effect occur? And did Venus ever have an ocean? That is an outstanding question. So it's time to go back to Venus. There are 2 missions, a Rocket Lab and MIT collaboration that will hopefully create the next set of missions, the Morningstar missions to Venus, they're called. And the Indian Space Agency has something planned as well for later this decade. But there are 3 future missions that have been selected and are in development between NASA and the European Space Agency. This is Da Vinci, Veritas, and Envision. However, the budget in the US has been quite unreliable for science lately. So these 2 missions and some of the third one are continue to be a little bit at risk. So one of these 3 missions that were selected, they were all selected around the same time, which was very exciting because it's definitely time to send more spacecraft and explore this planet more. The first one is a European Space Agency mission called Envision, and it's going to use a lot of different instruments from a geophysics standpoint and use a combination of these observations at different wavelengths to study the coupling of different processes associated with geologic activity. And these are going to be for more sort of targeted areas on the surface. And I helped select some of them. I was part of the team that investigated that. It will hopefully have some sort of imaging radar that will do targeted investigations and a sounding radar as well that will be able to look under the surface for buried craters, maybe old lava flows, look at these highly deformed tessera terrains and see if there's any sort of interesting features in the subsurface. So basically looking for past events that are now hidden from the surface view. The atmosphere is also an ongoing issue for getting multispectral data, but there are some very targeted multispectral instruments that might be able to image the surface at different wavelengths that will give us some idea of the composition and what kind of makes up the surface. The next one, Veritas, is a NASA mission that was selected. And on paper, Envision and Veritas look very similar, but its goals are to capture a more global coverage and provide more of a foundational data set for comparing and contrasting Earth to Venus on large scales, and support other science that really requires that global coverage, like crater counting. The last one is the Da Vinci mission, and that's a NASA mission. There's going to be an orbiter and an atmospheric entry probe. So the orbiter in the upper right will observe the atmosphere as it descends, and will also observe the surface of Venus at infrared and ultraviolet wavelengths as it cruises down to the surface in an area called Alpha Reggio. And there's actually lots of lab work to calibrate these future measurements to make sure that we will be able to make sense of the data that we get back. The entry probe on the left here. Oh wait, sorry, that was the orbiter. Yeah, orbiter was here. Yeah, so it's going to observe the atmosphere, and then the entry probe will do the imaging as it descends, and also take measurements of everything, but at a smaller scale. For Mars missions, when you're sending a spacecraft to the surface of Mars, there's something called the 7 minutes of terror, where you don't have direct contact with the spacecraft. You don't know what it's up to, if it's okay, and you have to wait 7 minutes to get back a sign that it made it. On Venus, for some reason, this is an hour-long hour of terror. So that will be creating a lot of anxiety for the engineers when this mission finally goes. So I've introduced my work as a planetary scientist and representation of planetary science in society. I've gone over Venus in historical and modern contexts, and I've given you a crash course on radar, hopefully. And I've introduced the next generation of missions and questions that they aim to answer. And hopefully I've convinced you that Venus is not Earth's twin, but it's still pretty cool nonetheless. So thank you.
Thank you so much for that amazing talk, Megan. There were some incredible images of Venus there that I've never seen before, and it's shameful that we haven't sent any missions to study the surface of Venus since Magellan in the 90s. So everyone, please send in your questions for Megan. We have a few here that we can get started with. The first question, Megan, is, are the pancake domes elevated above the surrounding terrain or collapsed below it?
Oh, that's such a good question. I was about to mention that. It's sometimes, so I have the image inverted so that high rate of returns were in dark there, and they are elevated above the surface. But sometimes when you're looking at data and you're not used to seeing it, your eyes might flip it and it might be inverted. So they are above the surface. They're like pancakes that are sitting on top of the surface.
Okay, great. Thank you for that. Next question, how or does this research affect our understanding of Earth?
Oh, yeah, that's a really good question. I've always been interested in, Venus and the Earth are they're in the same solar system neighborhood, same building blocks, as I mentioned. I feel like they should be a lot more similar than they are. Maybe more Mars-like even. Maybe if there was less of an atmosphere, they might be more similar. And I feel like when aliens look at our solar system, if they ever do, and they see that there are these two planets, maybe Mars as well, could be in this category, that are kind of in the Goldilocks zone. So they're not too far from the sun, they're not too close. We're all getting good solar insulation from the sun, we're getting good energy. Why did they end up so differently? And Venus, the modeling of the Venusian atmosphere actually helped us refine our view of the idea of a runaway greenhouse effect in their atmosphere. And that could, very small possibility of it happening tomorrow, but in the future sometime, if we put more CO2 into the atmosphere, we could cause a runaway greenhouse effect on the Earth as well. So I think Venus kind of serves as a laboratory for exoplanets, but also atmospheric dynamics, and as a reminder to treat our planet well.
Absolutely. There are a couple comments here as well. Someone mentions great X-Files episode from that site. I presume that was Arecibo, maybe.
Okay. I think I watched that a long time ago. I need to watch it. Yeah.
Another comment. Magellan was actually built out of spare parts. The antenna is a spare from Voyager.
Oh, that's cool. That makes a lot of sense. There are a lot of like heritage instruments that are used for a lot of spacecraft missions. So they might recycle parts and they might recycle concepts as well. That's good to know. Voyager also provided a really great images of the entire solar system, both of them.
Going back to the volcanoes on Venus, question here is, what is the composition of its lava? Or is that one of the open questions we still need?
Yeah, so the composition of all the volcanoes, or specifically the pancake domes?
Lava. You mentioned lava flows.
Yeah, that's kind of an outstanding question. We more or less assume that it's basaltic, like on Earth. So the lavas that you would see in Iceland or Hawaii. So not very viscous, not very silicic, as we say. So lower viscosity, creating these like very, very long flows with low bay edges, sometimes creating the volcanoes depending on emplacement conditions. So we assume they're basaltic. If we did see anything different with these upcoming missions, that would be very exciting, because there's a big implication if we see, for example, something that has more of silica content. On the Earth, high silica lavas are created from plate tectonics and the interaction with water. So that might have interesting implications for what we believe is happening on Venus. But for the most part, everything's made out of what is probably basaltic lava. And the composition data returned back from the Venera landers is kind of consistent with that, with some interesting anomalies as well.
That's really, really interesting. So much still to learn about Venus.
Yeah, definitely.
There was in recent years there was some reports of phosphine detected in the atmosphere of Venus. Any thoughts on that research and that discovery?
Yeah, so phosphine is really interesting because it's atmospheric stuff. I'm not a super expert on it, but it was very interesting because on the Earth, phosphine, as we know it, is produced by biology and by life. And if it was in the atmosphere of Venus, we would expect it to be broken down or just disappear very quickly. But the fact that we were seeing detections of it in the data, telescopic data of the atmosphere specifically, suggested that it might have an origin where it was continually being replenished. I think there are still some outstanding questions. There was interesting scientific debate after those results were first published based on the data that was used and the data processing as well. So I encourage everybody to go look into that and tell me what you think.
Remain skeptical, and more research is always needed. Absolutely.
I think so. More research and more data processing too.
I remember you mentioning to me there is a place in Venus's atmosphere. I'm not sure. I don't think you mentioned this in the presentation, where the temperature is like not 464 degrees. It's really only that temperature at the surface. But in the upper atmosphere, there's a layer where it's comfortable.
Yeah. It's I think it's about 50 kilometers up, where the surface, or the temperature and the pressure of the atmosphere is like 1 bar. So it's like on Earth, and the temperature is actually pretty mild too, relatively. And so that's where I would expect we would find life, maybe in the clouds. And I think if we ever send balloons to Venus, for example, as to explore the surface, or maybe explore the atmosphere, maybe do some imaging and atmospheric composition, I think we would probably send those balloons there so they wouldn't have to deal with the extreme conditions.
We have a couple questions sort of related to Venus's tilt and its retro rotation. What produced the retro rotation, and why would Venus rotate um, uh, on its side relative to the Sun versus at 23-degree tilt like Earth or Mars?
Oh yeah, so it doesn't orbit or doesn't rotate on its side, but it does rotate backwards. And so the rotation is the one that produces the days and the nights. I don't know, actually. It doesn't really make sense from an angular momentum perspective if you're assuming everything was coalesced from the pre-solar nebula. Um, and it's also very slow rotation. It's not tidally locked with the sun, which we used to believe, but it is very slow. And I think that also is taken into account of models of the early Venus atmosphere and surface conditions, and probably one of the reasons it might have a runaway greenhouse effect today is because one side is always receiving that intense solar insolation and the other side wasn't. But now the atmosphere kind of insulates everything and creates a near steady temperature. But I'm not actually sure why, and I don't know if we know why it rotates backwards.
I think I remember reading something where it's tilted like almost like a 180 degrees
Oh
almost.
yeah, I
So
guess technically,
it's
yeah,
like
yeah,
it's like our reference frame is that this is up, so it's rotating the other way relative to up, but it's actually like this. But I don't know why it would be so tilted like that. Like how could it be tilted by that much? Like most of the planets in our solar system have tilts because of impactors and things that happened during the early solar system formation and things like that.
yeah. Like
But
Neptune, right? Is it Neptune? It's 90 degrees,
it's
or is it?
Uranus
Okay.
is 90 degrees, yeah,
Yeah,
90 maybe, yeah. It's around about there, but yeah, it's all the tilts are quite varied. Um, but Venus is curious in that respect, and it's kind of doing its own thing backwards.
it
Um,
really is. Yeah.
yeah, we have I think two more questions. Um, um, why did it lose its magnetosphere? Why cool more than Earth?
Why did it lose its magnetosphere, and
It says why cool more than Earth.
why cool more than Earth?
Yeah, I think sort of yeah, I
So
think that relates to losing the magnetosphere and an impact on the atmosphere.
yeah, exactly. So it might not have an active dynamo underneath. So the liquid inner core might have solidified by now. We don't know if it ever maybe it had a magnetosphere at one point. We don't know because on other bodies we can sort of measure a crustal remnant field on the surface, so we can maybe the body doesn't have a magnetic field now, but it did at one point, and it was able to magnetize the rocks on the surface as they formed. But on Venus, it's so hot that it might erase that signal.
Mhm.
So yeah, it could be. There are a lot of modeling out there to explain, like maybe the dynamo shut down at some point. Um, Maybe it just cooled too fast. Maybe our magnetic field is somewhat of a fluke. So yeah,
Yeah, because we know Mars doesn't really have a global magnetic field either.
yeah.
There's a question here um, tying into kind of extremophiles and sort of hydrothermal vents at the ocean floor on Earth. The question is asking, are the conditions in the atmosphere of Venus similar to the black smoke that there's these underwater hydrothermal vents that have microclimates with active biology, these extremophiles that can live in these?
Oh yeah, extremophiles on the Earth are really interesting, and I think there was a period of time where we were so surprised to see life thriving in these areas on the Earth. And there's actually large parts of the ocean, especially the deep ocean, where that we haven't explored, um, including these vents where there is um, sort of either magmatic activity or heat coming from the surface and interacting with the material on the surface and heating up the water around these vents. And then we do see life around them. We the life that was going to persist on Venus would have to be okay with no water. There's no water on the surface. It long evaporated away. And it would have to be okay with that really sort of crushing atmosphere that makes the air so thick that it's almost like you would feel it. The CO2 is almost supercritical, so you would feel a higher viscosity of air even, and so it would have to be okay with that. That's definitely some of the things to keep in mind for future missions, if there are any areas of Venus that we would want to explore in that way, kind of like we do on the Earth when we're looking for life in extremophile environments.
Mm-hmm. And for sure, and life on even extremophile life on Earth, I believe, needs liquid water, and so that is something that we have not yet found, is that kind of extreme life that relies on, that's able to survive without it. So typically, that's why we're always looking for water. So where there's water, we can maybe perhaps one day find life, or there could have once been life. I think there's one last question here, and then we'll wrap up. Yes, this question actually connects to something you said in response to another question with relation to the atmosphere. Why would balloons be a better option than drones to study Venus's atmosphere? Recognizing that you don't necessarily study the atmosphere, you study geophysics of the surface, but with relation to this question, to the best of your knowledge.
Yeah, I think there's quite a few reasons why. So the atmosphere of Venus rotates much faster than the planet does. And so even though there's probably very little wind at the surface, there are really high winds in the atmosphere higher up. And you could send a balloon there and you could just let it bop around in the atmosphere and let the atmospheric winds take it around with very little energy needed. A drone would be cool. I don't know if drones can fly in a supercritical, super thick atmosphere like that, but it might be really hard to manufacture electronics that can withstand and make the rotors rotate and everything and all the systems function in either the surface temperature or pressure environment or the really corrosive sulfuric acid droplets higher up in the atmosphere. I think that would be harder. So it might be just easier to create a balloon and let it sort of go where the winds in the atmosphere take it. And I know there are quite a few white papers out there to describe the balloons and this concept. But I would love to see one with specifically a drone radar maybe for Venus.
Thank you so much, Megan, for your incredible talk. We're getting some lovely comments and gratitude in the chat here. Very interesting talk. Thank you. Thank you so much, Megan. Time well spent. Most interesting indeed. Thank you so much for sharing. And so everyone, please join me again in thanking Megan for joining us this evening. And with that, I would like to introduce the RASC Toronto Centre President, Scott Masterton, who will give some closing remarks. Thank you so much, everyone, and have a great evening. Here is Scott for the announcements.
Well, thank you, Rachel, and thank you to Megan for that very interesting and obviously provocative, as far as questions are concerned, talk. I'd like to let you know that I would like to welcome you, of course, and thank you for viewing our presentation online, and let you know that the Speakers Night is one of the two types of meetings we conduct. The other one is a RAN, or Recreational Astronomy Night, and that is in person and online, unlike tonight, which was exclusively online. And so we would encourage you to join us every couple of weeks for those events. And if you're able to come to the university, You can observe the see the Carswell Observatory by a tour on Wednesday evenings during the winter before the RAN, and it's a very interesting tour. I've done it myself, and you'll see the 1 meter telescope. Now, there are activities at the DDO through the upcoming 2 or 3 weeks. March break 2026 on March 21st at noon to 2 p.m. at the DDO. There's Sun and Fun, and you can go online to explore the costs and who's eligible to attend. The Millennium Square Public Star Party, March 27 or 8, depending on the weather. Go to the site to get information on Go No Go. All are invited. It's at Millennium Square, south end of Liverpool Road, next to Frenchman's Bay. And the DDO Astronomy Family Night is also occurring March 27th, 8:30 to 10:30. It's an in-person event at the David Dunlop Observatory. Go online, get the information and timing for that event. Also at the DDO, Sunday Stargazing for March 29th. It's a 1-hour event between 12:30 and 1:30 at the Dome. And we would invite you to safely view the sun through our available telescopes. Recreational Astronomy Night, April 1st, April Fools, is the next recreational astronomy night, and tune in later to find out exactly what is going to occur. We would like to let you know too that the Carr Astronomical Observatory, or the CAO, available to members, is open year-round, and you would have to go to the bookings site indicated here to arrange a visit. I did understand that more recently the road is washed out, and so for the time being, there's a temporary. It'll be temporarily unavailable because the road is not continuous or safe to travel. But we'll be fixing that. Also, we would encourage you, if you're interested, to join the RASC at the membership site on the national office website. And of course, once you're a member, you can volunteer to help us out on our various activities and outreach events for the public. And I would thank you for joining us tonight, and have a great night.